Okay, so we've looked at linear data. Linear data is going to have a constant rate of change over and over again. We talked about that on the first couple days of school, that if your table is consistently increasing the x's and the y's by the same amount every time or decreasing, then that tells us it has a constant rate of change, and that's what makes it linear. So that's when your data is really nice and it falls into a perfect linear relationship. But in real life, a lot of times that doesn't happen. When we're collecting data on naturally occurring things, or if we're timing something, we might get close to a linear model, but it's not going to be exactly correct. And that's where we end up having to look at what we would call a scatter plot. And I know you've seen these before, you do these in science. So the way that we find a line of fit is what we're trying to do is we're going to have our scatter plot, and our scatter plot is going to have a bunch of notes around, or not notes, sorry, it's going to have a bunch of points, and Shay's asking me a question, and so then we're going to draw some line that seems to get as close to all of those data points as we possibly can. That's what we're trying to do when we find a line of fit. When we do this by hand, it's just called a line of fit because it's one of many. We might all get different answers. When we use technology, that's when we would call it the line of best fit, because that's when we're using technology to actually find the one that is the very best line for that data. That we can't do by hand. We have to have a computer help us with that, and that's part of what we're going to look at today. All right, so there are 4 steps that we're going to follow. Most of these are going to seem exactly like what we did yesterday. So the first one is we're going to create a scatter plot of the data. So I'm going to have a bunch of dots that appear to go in some sort of pattern here. That's step 1. Then we're going to sketch the line that most closely follows the data. We want to try to split that set of points so that there's about as many points above the line as there is below the line. We want to try and average through all of those points. From there, once we do that, then the only thing we care about anymore is that line. We don't care about any of those blue dots that are scattered around. The line is what we're going to find in the equation 2. So we're going to follow the same steps of what we did yesterday. I'm going to find 2 points that are on that line, and I'm going to use my slope formula. So remember, that's y2 minus y1 over x2 minus x1. Once I have the slope, then we're going to use the point slope formula, y minus y1 equals m times x minus x1. Put that into slope-intercept form, and that's how we're going to find the equation. Okay? So if we look at number 4, the example down here, what we're going to do is we're going to compare femur length in centimeters, that's one of the bones in your leg, to your overall height in centimeters for several different people. Now, people vary, so we're not going to expect it to make a perfectly straight line, but we're going to see if it's close to a straight line or not. And then if it is, then we'll write an equation of the line of fit that we're going to pick and use that to estimate the height of a person whose femur is 35 centimeters long. So first thing I'm going to do is set up my graph. All right, by the magic of technology, here's my graph. So a couple of things to sort of point out to you here. The way I decided on my scale was I looked at what the furthest I had to go was. So for femur length, you can probably hear my dogs in the background. Sorry, that's going to be a normal occurrence. But 50 is what I had to get to. So I counted up the squares, saw that I had, how many? 5, 10, 15, 20, 25, 27 squares. So I figured if each one was 2, then I'd be able to get to 50. So each of those squares is 2, but instead of counting 2, 4, 6, 8, I just only marked every 10th interval because it can get really crowded when you try to label every single one of those squares on a graph that tiny. I did the same thing with the height. I saw that the highest I had to get up to was 195, or roughly 200, and so in that case I decided to count by tens based on the squares that I had. The other thing I want you to notice is that I do have labels with units on each of my axes. That's really important. Make sure that you do the same thing. So I'm going to go through now and plot each one of these data points. So, for example, my first one, I'm going to treat each of these as an ordered pair. So 40, 170. So I'm going to go over to 40 for femur length and go up to 170, which would be right here, I think. Whoops. Right there. Whoopsie. Sorry, I'm having a moment with my technology. It doesn't want to let me draw a dot. So here it is. That is 4170. We're going to go through and do each ordered pair in that scatter plot. So go ahead and take a second to do that, and I'll be done in a flash. Ta-da! Here are my data points. That's what I get when I graph all of those. And we can see they don't make a perfectly straight line, but they are close to a straight line. And that tells us that, yes, this data probably is a linear relationship. So now what I'm going to do is I'm going to take a ruler. Don't try to freehand it or your line is not even going to be close. And I'm going to draw a line through here that goes approximately right down the middle. So I'm going to try to make sure that it goes through as many points as possible with about the same number above as there are below. So that might be a line that looks like this. Fairly close. Okay, so that's the first couple of steps there. Now what we need to do is we need to choose 2 points. They don't have to be any of the black points from our scatter plot. They need to be points on the red line. Now, it would be nicest if I picked points on the line that appear to go right through where the box is crossed. So this purple point right here looks like a good one. That looks like 36, 160. So I'm going to choose that point, and then it looks like there's another good one at about 20. That one maybe isn't great. Let's see. Do I have one that's better? I think right here looks pretty good. Let's see. That's 24, 130. So those are the two that I'm going to use to figure out my slope. So remember, we can go ahead and call these x1, x2, y1, y2. And then I'll want to go ahead and take those values and plug them into my slope formula. Okay, here's what I get. When I do the subtraction and plug into that formula, I get 30 over 12, which is, I put approximately, but it comes out evenly. It's exactly 2.5, so you can put equals right here instead of little squiggles. So that's the slope that I'm going to use. And again, if I think about that, that tells me it's a positive slope, which is exactly what my line shows. And if we think about what that means, that tells us that for every centimeter longer your femur is, that your height is going to be 2.5 centimeters taller. That's what that rate tells us. So now that we have our slope, we are going to use the point slope formula to come up with the equation of the line. So again, I'm going to substitute here, here, and here. It does not matter which two of these points we use. I'm going to choose this one simply because the numbers are smaller. So I'll go ahead and substitute. And then from there, I'm just going to do my algebra to get the y by itself. So this is what I get. And if we look at our y-intercept here and compare that to our graph, here's 70 right here. That's pretty dang close. It might not come out exactly the same because this is an estimate, but it's going to be pretty darn close there. And mine came out pretty much dead on, so I feel like I'm on the right track. If I want to see the height of someone whose femur is 35 centimeters long, then we are going to take 35 and plug it in for x because that's femur length. And so here's what we get. So I can expect a height of about 157.5 centimeters for a person whose femur is 35 centimeters long. Now, it may be a little less than that. It may be a little bit more than that. The line of fit is just a way to predict what it'll be close to. if you ever take statistics, you'll look into a lot more detail as to how close that number is actually going to be and what your margin of error is there. So that's how we can do this by hand, which is pretty tedious, and nobody wants to do all of that work. So luckily, the computer will do this for us, and it's even better because it gives us the best information. So what we're going to do is, if you go on to this next page, a couple of things that we want to talk about first. The first is the correlation coefficient, okay? This is a number that is represented by R. I'm not sure why we use R, but that's what it is. It's always going to be a number from -1 to +1, and it tells us how well a line fits a set of data. Now, I don't know if you can kind of see where this gets cut off down here, so you might want to fix this. This would be strong negative, no linear, I'll get the hiccups, or strong positive is what those are going to say. So a positive talks about the slope. Negative also talks about the slope. So strong positive means my points are pretty much in a perfectly straight line that has a positive slope. Strong negative, same thing, except the slope would be going down this time. No linear, no correlation would mean it looks kind of like a shotgun hit it. So it's just scattered all over the place. Now we can get numbers somewhere in between there, like say positive 0.5. Well, that would be points that might not be quite in a straight line, but they're close. Negative 0.5 would be the same thing. So the closer you get to +1 or to -1, the better your data set is fit by a line. The closer you get to 0, the worse the relationship is there, okay? Now, we are going to use, I don't know if you've used this in other classes, but the website is www.desmos.com. And we are going to use the feature that'll show us how to do the line of best fit. I'm going to put that in a separate video so you can get the instructions whenever you need them if you want to do this again. So go ahead and get started on part 2.